All right, so welcome back. So the goal of this video and the following will be to do a few examples from chapter 4, kinematics in 2 dimensions. All right, so let's take a look. Here's the first example. We're told a particle's trajectory is given by the following. A trajectory of something is given by x. The position in the x direction is x equals to 1/2 t cubed minus 2t squared. And the y as a function of time is 1/2 of t squared minus 2t. And so let me write the position vector right away. The position vector, as we know, is x as a function of time, I hat, plus y as a function of time, j hat. That's the position. And let's just write it explicitly. So r will equal to 1/2 of t cubed minus 2t squared, and I hat, plus y of t, which is 1/2 of t squared minus 2t j. All right. We haven't even read the problem yet at what they want. So the first question is, what is the particle's position at t equal to 0 and at t equal to 4? What's the particle's position and speed? So find r of t and the speed. We'll find the velocity first, and then the speed will be the magnitude of the velocity at t equal to 0 and at t equal to 4 seconds. Well, let's find r at t equal to 0. R at t equal to 0. Oh, we go to the position and plug in 0. If you plug in 0 here, you get 12. 0 cubed is 0, and squared is 0, so you get just 0 I hat. And then here, if you plug in 0, you just get 0 plus 0 j hat. It means the particle is at the origin. It's just right at the origin. X is 0 and y is 0. How about at 4? At 4 seconds. At 4, well, let's see. You plug in 4 seconds here. 4 cubed is 64, and 64 over 2 is, let me write it down before I forget, 64 over 2 is 32, minus, let's see here, 4 squared is 16, and 16 times 2 is 32, so 32 minus 32, I hat, so that will give us a 0, and then plus, this one here, 1/2 of 4 squared, 4 squared is 16, over 2 is 8, and then minus 2 times 4, that's 8, and so we get times j hat. So again, it's at 0, 0. 0 I hat plus 0 j hat. So the particle is at the position 0, 0 at both at t equal to 4 seconds, at t equal to 0 seconds, and at t equal to 4 seconds. So it wandered around and then came back to the same position after 4 seconds. Came back to the origin. Okay, what's the next thing? The next thing they want v of t. Let's find v of t and then the speed. So we know that v as a function of time is the derivative of position versus time. And let's take derivative of position with respect, this is position with respect to time. Let's take the derivative. Derivative of 1/2 of t cubed, the 3 comes down, so it becomes 3/2 t squared. So 3 over 2 t squared. And then minus, derivative of minus 2t squared is minus 4t. 4t, and that's in the I hat direction, in the x direction, plus derivative of this with respect to time, a 2 comes down, so you get just t. T minus, derivative of 2t is just 2. J hat, okay. So what's the velocity at 0 seconds? So the velocity at t equal to 0, it is, you plug in 0 here, so you get 0 I hat, and you plug in 0 here, you get negative 2 j hat. So the magnitude of velocity at t equal to 0, that's the speed at 0 seconds, is you square the x, you square the y, and then add them. So you get 0 squared plus negative 2 squared, square root, and that's just 2. So it's 2 meters per second. That's the speed at t equal to 0 seconds. What's the velocity at t equal to at 4 seconds? I plug in 4 here and see what happens. Let's get the velocity at 4 seconds, and then we can get the speed. Once you find the velocity, the speed will be the magnitude of that. So it will be what? Plug in 4 here. You get 4 squared, that's 16. 16 over 2 is 8. And 8 times 3 is 24. So 24 minus. And then 4 times 4 is 16. And then plus t minus 2. That's 4 minus 2. And so you get 4 minus 2 j hat. And so the velocity at 4 seconds will be 24 minus 16 is 8 I hat. And then 4 minus 2 is 2 j hat. That's the velocity at 2 seconds. Let me make sure that I have it correct. 8 I hat plus 2 j hat. Yes, that's correct. And so what's the speed at 4 seconds? The speed at 4 seconds would be the magnitude of velocity. And so that would be the x component squared plus the y component squared, square root. So it'll be 8 squared plus 2 squared, square root. And that's what? 64 plus 4, it's 6 square root of 68. And the square root of 68 is what? 8.3. Approximately 8.3 meters per second. And then part B, they want the direction of the particle's motion measured as an angle from the positive x-axis. What's the direction of the particle's motion? Well, here is the particle at t equal to 4 seconds. What is the direction of the particle's motion? Well, or actually at 0 seconds first. Let's do direction of motion, part A. Direction of motion will be the direction of the velocity. That's if you're heading this way, your velocity is that way. It's the direction of motion. It's the velocity. Please ask me during class if that's not really clear, why the velocity is the direction of motion and not the position. The position is merely the location in space. So here is your position. You could be here, but your trajectory, let's say you're moving like that. So your position is here, but your direction of motion is this way. It's the velocity, it's the tangent there. So anyways, it will be if you want theta, it will be the x component of velocity divided by the y component of the velocity inverse tangent. I'm sorry, it will be the y over the x inverse tangent. So for the first one, at 0 here, the velocity only has a y component, and it's negative. The velocity points in this direction. It's 0 I hat minus 2 j hat. So it points this way. The velocity points that way. So it is at negative 90 degrees. So at t equal to 0, the velocity is just straight down. So that's the direction of motion. So it's at negative 90 degrees below. So it's 90 degrees below the positive x-axis. Or you can say it's at 270 degrees from the positive x-axis, or negative 90 degrees. Both, all of them would be correct. So for and then for at t equal to 4 seconds. What's the velocity? Well, the velocity at t equal to 4 seconds is 8 I hat plus 2 j hat. So it's 8 units in the x direction, only 2 units in the y direction. So the direction of motion is that way. So this is theta. And theta would be the opposite of, the tangent of theta is opposite of adjacent. So theta itself will be tangent inverse of the y component of velocity over the x component of velocity. So the tangent inverse of the y component of velocity is 2 and the x is 8. So it's 2 over 8 or a fourth. And so that turns out to be, if your calculator is in radians, so it would be 14 degrees above the x-axis, above the positive x-axis. All right, so that's the first problem here. All right, so that is just motion in 2 dimensions in general. I would like to do one for projectile motion now. Make sure everything's going fine. All right, so here is a projectile motion problem. So you have a, you put your example. You have an Olympic athlete who throws something at a speed of 12 meters per second at 40 degrees from the horizontal. So here is the athlete. She's here. And she throws something, she throws it, so here's her hand, and throws that thing in this direction. Let me call, this is v initial, that's the magnitude of velocity. They said it's 12 meters per second, and they're telling us that the angle, she throws it at 40 degrees above the horizontal. And what happens to this thing? Well, this thing will, here is the ground. The ground would be the x-axis. And let me choose our coordinates. This will be the y-axis. And so this thing is thrown, and then it will come and then reach here. And that's the range of motion. And the question is, where does it land, given that it was thrown from a height h equal to 1.8 meters. Make sure it's correct. Yeah, 1.8 meters. So she throws the thing like this, from 1.8 meters, and it goes and then lands somewhere. So the initial y position, let's choose our origin here. So the initial x position, so x initial is just 0, it's on the y-axis. Y initial is from here. If this is the origin, this is 1.8 meters. So it's at 1.8. X final, I don't know what it is when it lands. Y final, I know it lands on the ground. So that's at 0 height, so it is 0. And let's also further write down the velocities. V initial is 12 meters per second, so Vx initial will be V initial times the cosine of theta, and that is 12 times the cosine of 40 degrees. And then Vy initial will be V initial times the sine of theta, which is 12 times the sine of 40 degrees. Sine of 40 degrees. And we have to use our calculator here to find the sine and cosine. Unfortunately, I don't have them. So let me use my calculator. So first, 12 times the cosine of 40, 12 times the cosine of 40, I get 9.193 meters per second, of course, it's a speed. And then 12 times the sine of 40, and that's 7.713. By the way, the whole problem here is in three significant figures. It's really 1.80, this is 12.0, and so on. So I'm keeping 4, but at the end I can always throw 1 away. As a good rule, you should always keep 4 significant figures, or even 5, and then you can always get rid of them. You get rid of the insignificant ones at the very end. So that's that. Then I would like to know where it landed. Well, I know that there is acceleration in the y direction, but there is no acceleration in the x direction. So the speed in the x direction is 9.193, and it will always remain at 9.193 throughout the motion. So even at the peak here, at the peak, the y component of velocity will be 0 because it's not getting higher and it's not getting lower at the very peak. However, the x component of velocity is still 9.193. So at the peak, the y component of velocity is 0, but the x component of velocity is still 9.193. Here, the x component of velocity is still 9.193. Here, the x component of velocity is still 9.193. However, here versus here versus here, the y component of velocity, they're all different. Okay? So, I'm going to solve this by saying I have to find the time first, and once I find the time, multiply time by speed, and that gives me the distance along the x. So I would say, I know that y final is equal to y initial plus v initial in the y direction. I wrote it vy initial. Vy initial times the time minus 1/2 gt squared. That's one of our equations of kinematics. And g is 9.8. So y final is 0. Y initial is what? It was 1.8. And then Vy initial is 7.713 times t minus half of g is g is 9.8, so half of that is 4.9, so minus 4.9 squared. So you have a quadratic equation to solve. Well, use your quadratic formula solver to solve for this. And this will give you a t, will give you a positive value for t, that's the t, it hits the ground here, or a negative value, because if we go back in time, suppose if it follows the same trajectory, it will be at the ground. So, but we started at t equal to 0, and the time goes on, so we will take the positive time. So let me check out what the answer was for the time. When you solve for the quadratic, you got t equal to negative 0.206. This would be thrown away because we started at t equal to 0 and on. We know what it means. 0.206 seconds, if it follows this path, it was at the ground, but we don't need this. Or the solution that we take is the 1.780 seconds. That's the time. So now, it is flying, and at every moment it's making progress to the right. So how far to the right did it go? Well, we know that x final is equal to x initial plus vx initial times the time. It's almost like this equation, but there is no acceleration in the x direction, so we stop there. And so you get x initial started being 0, v initial in the x direction started, well, it's always 9.193, and the time is 1.78. Multiply them together, and you get approximately 16.4 meters. 16.4 meters. Sounds good. So we'll go to the next problem. So here's an example where we have a projectile motion, and it's maybe a windy day or something. So there is acceleration in the x direction that causes it to slow down. So it says a projectile is launched from ground level at an angle theta and speed v initial into a headwind that causes a constant horizontal acceleration of magnitude a opposite to the direction of motion. They didn't have to say it's opposite to the direction of motion. It's obvious because they say it causes it to slow down, so it better be opposite to the velocity in the opposite direction of motion. Anyways, find an expression in terms of a and g for the launch angle that gives the maximum range, and then if this acceleration that's in the x direction happens to be 10% of g, what is the maximum, what is the angle that gives the maximum range? What is the angle for maximum range? What is the angle for maximum range? What's the angle for maximum range? So how are we going to solve this? So this is a problem where you have an acceleration in both the x and the y direction. And so we know the following. So here is like what's going on. Here is x, here is y. Our projectile is fired this way, and then it goes and then does something like that. Eventually it falls down. And so we know that, this is the solution here. There is acceleration in the x direction, so x will equal to x initial plus v initial in the x direction times the time, and then plus 1/2 of the acceleration times the time squared, but it's negative because it's slowing it down, minus 1/2 of the acceleration in the x direction times the time squared. It's a negative acceleration because it causes it to slow down. And then for the y, it is y equals to y initial plus vy initial times the time, and then minus 1/2 gt squared. Because, so again, if the particle is moving this way, we know that the acceleration is this way. And our particle is, I'm assuming it's going this way. If we shot it this way, then the acceleration would be that way. So this acceleration is this way. The acceleration due to gravity is g, or is negative g, and it's downward. Okay. So now we need to simplify this, and since we have to maximize, we have to eventually basically take either take a derivative and work with trigonometry. All right. So we're going to use our initial conditions. X initial is 0 and y initial is 0, and this is the angle theta. So this is 0 and this is 0, and y final will also be 0. So this is 0. So let's start with the equation for the y first. So we will start with this one. So I get 0. This equation here, I get 0 is equal. Vy initial is just v initial times the sine of the angle theta, which is here, v initial times the sine of the angle theta. So it's v initial times the sine of theta, whatever that theta is, times t, and then minus 1/2 gt squared. So we will divide by time, in both. The time will be sometime later, so it's not going to be 0. So we divide by t and divide by t here, and then solve for t. So we get the time of flight will be, what? 2v initial sine theta divided by g. And then we're going to use this time and place it here. So I have x will equal to vx initial, that's v initial times the cosine of theta, times the time, right? And here times the time, which is 2v initial times the sine of theta divided by g. Yes. And then minus 1/2 of the acceleration in the x direction times the time squared. But t is 2v initial sine theta over g squared. Yeah. Okay. So that's that. And we can simplify this a little bit. So I get x will equal to 2 v initial times v initial is v initial squared. Actually, let me take the 2 out, because 2 sine theta cosine theta is the sine of 2 theta, sine 2 theta. That looks a little simpler. Divided by g. Okay. And then here I have minus. 2 squared is 4, but there is a 2 here, so this becomes, there is just a 2. And then a. And then v initial squared, so v initial squared. And then you square the g, you get g squared on the bottom. And then times sine squared of theta. I think I have it correct. Let me just make sure I have everything good. That looks correct, I think. Yeah, it looks fine. Yeah, that looks fine to me. Yeah. Okay, so now what are we going to do with this? We have our we have x, and x is a function of theta, so it's some function of theta. And what do you do if you have a function and it depends, if you have f of x and you want to find where f is maximum or minimum? Well, you take the derivative of that function with respect to x. So here x is a function of theta, so we'll take the derivative of x with respect to theta and then set that equal to 0, and that will give us the critical point. Okay? So we'll take dx d theta and see what happens. Dx d theta and then set it equal to 0. Let's take the derivative here. V initial is constant and g is constant, so I have just that. So I just have derivative of sine is cosine, so it will be v initial squared over g times the cosine of 2 theta, and then times the derivative of the inside. Derivative of 2 theta with respect to theta will just give me a 2, so there is a 2 here, and that's it. And then here I have minus 2a v initial squared divided by g squared. And then what's the derivative of sine squared? Well, it's 2 sine theta, and then the derivative of cosine of sine is cosine, right? And then you set this equal to 0. So derivative of sine squared, you have to take the derivative of the outside function. Something squared, the derivative of that is twice that something, and then times the derivative of the inside, which will be the sine, and derivative of sine is cosine. Okay, cosine, like so. Looks good so far. And yeah, so that looks good. And I'm going to, since there is a 0, I'm going to divide both sides by v initial squared, everything, so the v initial goes away. Divide everything by 2, so the 2 goes away. Multiply by g, so this g goes away. And we just have dx d theta is equal to the following. So here I have cosine of 2 theta minus, from here I just have a over g, and then 2 sine theta cosine theta is the sine of 2 theta equals to 0. And so let's move this to the other side and then divide by sine, or by cosine. So I have the following, I'll have this. Cosine of 2 theta will equal to a over g times the sine of 2 theta. Divide both sides by cosine and multiply. So if you multiply by g over a, by g over a, you have g over a on this side, g over a. And then you multiply, divide by cosine, you will just have sine over cosine is tangent, so you have tangent of 2 theta. That means 2 theta will equal to the tangent inverse of g over a, and therefore theta will be 1/2 of the tangent inverse of g over a, like so. Let me make sure I did not make any mistake. 1/2 tangent, yeah, that's good. So for the particular case, let me make sure I didn't run out of time. Yeah, for the particular case, if a is 10% of g, if a is 10% of g, it means, what is theta? So for part B, if a is so if it's 10% of g, so a is 0.1 g, we get theta will equal to 1/2 of tangent inverse of g over a, but a is 0.1 g, so g cancels. So you have 2 times tangent inverse of, this will be 10. 1 over a 10th is a 10. 1 over 0.1 is 10. So tangent inverse of 10 times 2 would be about 42. What did I do here? This should be 1/2. This is 1/2. Yeah. 1/2. So this is, I think they say 42 degrees. So it's at 42 degrees. So that's that. So that's an example of where you have air resistance. All right? And, all right, sounds good. I'm going to now pause this video and start the next one. Do a little bit of circular motion.